Today we will discuss the Hölder's inequality, and now we state the Hölder's inequality. Let x1, x2 up to xn and y1, y2 up to yn are real numbers. Then summation I from 1 to n mod of xi mod of yi less than or equal to summation I from 1 to n mod of xi power p raised to the power 1 by p into summation I from 1 to n mod of yi power q whole power 1 by q. This is the inequality for the which is the inequality known as the Hölder's inequality, and we prove this inequality for finite sums because here you can see that the sums the summations are from I from 1 to n. So the Hölder's inequality which we prove is for the finite sum. So let we start the proof here. And here one thing is to be noted that the Hölder's inequality is the general case of Cauchy-Schwarz inequality because in the Cauchy-Schwarz inequality P and Q they are equal to 2, but in the Hölder's inequality what is the condition of P and Q? Actually in the Hölder's inequality you must remember that P is greater than 1 and 1 by P plus 1 by Q equals to 1. So by this condition and this condition we can conclude that Q is greater than 1. Okay, so here are the conditions of P and Q. Now why Q is greater than 1 means how it comes. Since P is greater than 1 and implies that 1 by P is less than 1, so it means that P 1 by P is a number which is less than 1 and greater than 0. So this implies that 1 by P belongs to this interval, the open interval 0 to 1. So this also implies, since we have 1 by q equals to 1 by 1 minus 1 by p, so since 1 by p is greater than 0 and less than 1, this is a real number, so uh, ultimately this number 1 minus 1 by p is less than 1. Since 1 by q is less than 1, this implies q is greater than 1. So by this condition and this one, these two conditions, we can easily conclude that q is greater than 1. So we start the proof here. Here in this inequality, you can see that we name this inequality as equation 1. In equation 1, on the uh, right hand side, the summation I from 1 to n mod of xi power p whole power 1 by p, and summation I from 1 to n mod of yi whole power q whole power 1 by q. So on the right hand side, there are two possibilities. Might be we may have either this number summation I from 1 to n mod of xi power p whole power 1 by p equals to 0, or summation I from 1 to n mod of yi whole power q and raised to the power 1 by q equals to 0. So this number equals to 0, or might be this number equals to 0. There is one possibility. The second possibility is that this quantity and this quantity, both of them are non-zero. So the first case is that might be summation I from 1 to n mod of xi power p whole power 1 by p equals to 0, or summation I from 1 to n mod of yi power p whole power 1 by summation I from 1 to n mod of yi whole power q raised to the power 1 by q equals to 0. So might be these two are either this quantity or the other quantity, this one, equals to 0, or we may have both of them, this one or this one and this one, both of them are non-zero. So this is the first case in which uh, we suppose that either this one or this one equals to 0. So when we name this quantity equals to capital X, okay, and here we name this one capital Y, okay. If X is equal to 0, this implies that summation I from 1 to n mod xi power p whole power 1 by p equals to 0, and this implies that this summation I from 1 to n, that's equal to 0, and this is possible when each mod of xi or p equals to 0, and this is possible when each xi equals to 0. So we can say that this summation is 0. It is possible when each xi equals to 0. This implies that each xi equals to 0. Okay. Similarly, if y equals to 0, here you can write or if y equals to 0 implies in the same way each yi equals to 0. So this is our result. When x is equal to 0, then each xi equals to 0. Okay, then what happens? And when each xi equal to 0, in the equation 1, on the left hand side, this quantity equals to 0, which is summation I from 1 to n mod of xi mod into mod of yi. This is equal to 0, and on the right hand side, this quantity equals to 0, and ultimately the complete right hand side equals to 0, which is consist of these two terms, which is this is equal to 0. So in the same way, if we have y equals to 0, then each yi equals to 0. Then what happens? In the same way, on the left hand side, the quantity this quantity equals to 0, and on the right hand side this quantity equals to 0. So in this way, the inequality 1 holds in both the cases when the capital X equals to 0, you can say when capital X equals to 0 or capital Y, this is equal to 0, then 1 holds. So this is the first case, and you name it as the Roman one. This is our first case. Now we consider the second case, which is in Roman 2, when both capital X and capital Y are non-zero. This is our second case. When this one and this one are non-zero, so it means that what is x? X is equal to capital X is equal to summation I from 1 to n mod xi power p whole power 1 by p, and capital Y is equal to summation I from 1 to n yi mod or q whole power 1 by q. This is our capital Y. When both capital X and capital Y are non-zero, it means that X and Y, they are non-negative. Obviously they are non-negative because it is not possible that x and y are negative, because here is a mod. You can see the value of capital X involves the summation of all these modulus power p, and likewise in the capital Y, that's equal to summation of all these mod of yi power q. So uh, due to this modulus, x and y can't be negative, so the only possibility is that x and y are non-negative. So this is non-negative, and this implies that when x when x is non-negative, then what happens? When x is non-negative, then the only possibility is that obviously the uh, mod of xi for each I equals to that's equals to 0 or greater than 0, and similarly mod of yi is greater than or equal to 0. uh, I think you may write in this way, because uh, this is the obvious condition that mod of xi and mod of yi for each I equals to 0 or greater than 0. And so you don't write in this way, because this is the obvious condition that the modulus of xi and modulus of yi are non-negative. So you don't need to write in this way. This is obvious that obviously mod of xi mod of yi equals to sorry are non-negative for each I. So therefore for each I, xi mod over capital X, I think you write in this way. You don't I change the indices here. Instead of I would write k for each k. For each k where k is from 1 to n. So for each k, mod of xk over x is non-negative, and for each k in the same way, mod of yk over y is non-negative. So these two quantities mod of xk over capital X non-negative and mod of yk over capital Y non-negative. For these two quantities, we apply the Young's inequality for non-negative real numbers. So here we suppose this quantity as A and we suppose this quantity as B for our convenience. And what is the Young's inequality? Here the Young's inequality is stated as follows. What is the Young's inequality? When x and y are non-negative real numbers, then you write if this is better, then xy is less than or equal to x power p over p plus y power q over q. This is our Young's inequality with the same condition of p and q, that p is greater than 1 and 1 by p plus 1 by q equals to 1. So we apply this Young's inequality for our A and B, A non-negative and B non-negative for each k. So we apply this Young's inequality. When we apply the Young's inequality, so what we get? We get, you must follow this inequality, this one. So we have A, B less than or equal to A power P or P plus B power Q or Q. This is for each k. For each k, we have this inequality. So when we apply this, when we put the values of A and B here, so what we get here, A is mod of xk, you can write for each k here, mod of xk over capital X, which is the value of A, into value of B mod of yk over y. Less than or equal to mod of xk over x whole power p over p mod of yk over y whole power q over q. We just put the value of a and b in our Young's inequality. A and b. A is mod of xk over x. So here mod of xk over x into value of b. Sorry, value of b, which is mod of yk over y, less than or equal to a power p. So it means that mod of xk over capital X or p whole divided by p, plus in the same way value of b, which is mod of yk over y whole power q, uh, and whole divided by q. So this is our required equation, in which we put the values of a and b. So we again simplify. That's equal to mod of xk into mod of yk divided by x y. This is also for each y less than or equal to 1 by p plus 1 by q times mod of y k over capital Y whole power q. So here we put the values of capital X and capital Y. Which is mod of xk into mod of yk over capital X, and capital X is equal to summation I from 1 to n mod of xi power p whole power 1 by p into summation I from 1 to n mod of yi whole power q raised to the power 1 by q. And similarly on the right hand side we have 1 by p times 1 by p times mod of xk power p divided by summation I from 1 to n mod of xi power p whole power 1 by p. So here you can see that there is the power p. So due to this power what happens? This is p plus 1 by q times that's equal to, in the same way, mod of y k power q whole divided by summation I from 1 to n mod of yi power q raised to the power 1 by q. And similarly, due to this exponent, we have 1 by q into q. So 1 by q into q, here you can say that this quantity equals to 1, and also we have this quantity equals to 1. So we have mod of xk into mod of yk whole divided by summation I from 1 to n mod of xi power p whole power 1 by p summation I from 1 to n mod of yi power q whole power 1 by q. This is less than or equal to 1 by p. For each k we have this one. So this inequality number 2, it is satisfied for each k. So we can say that we have n number of inequalities, means for k is equal to 1, for k equals to 2, and up to so on for k equals to n. Equation number 2 is for k, means that in the same way, in particular we have n number of inequalities for k equals to 1, equals to 2, and then up to so on for k equals to n. So when we sum all these n number of inequalities, means how can we sum? We sum by adding the left hand sides and right hand sides of these n number of inequalities. So what we get? We sum with respect to k from 1 to n, because this one is the same for all k, and this one also, this quantity, means the numerator, this whole quantity is same for all k, and also this one and this one, they all are same for all k, so they are independent of k. So sum of this quantity from k equals to 1 to n, we have mod of xk into mod of yk whole divided by summation I from 1 to n mod of xi power p whole power 1 by p summation I from 1 to n mod of yi or q whole power 1 by q. this is less than or equal to summation k from 1 to n 1 by p times mod xk power p summation I from 1 to n mod xi power p plus 1 by q mod yk power q divided by summation I from 1 to n mod yi power q. Here what happens? Here we have, because this summation is for k, so it goes inside, because this quantity in the numerator, this one, it comes outside, because this is independent of k, so it comes outside this sum. Which sum? We have this sum k from 1 to n so this quantity comes outside here, and when it comes outside we have this one as required, summation I from 1 to n mod xi power p whole power 1 by p summation I from 1 to n mod yi power q whole power 1 by q less than or equal to, the summation is separated over here 1 by p, and this k depends on the numerator. Numerator is xk mod whole power p, and the denominator is same. Because this summation is depends on the numerator mod yk whole power q, and the denominator is same here. So this is our sum of all the n number of inequalities. So we sum n number of inequalities by adding the left hand sides and the right hand sides of equation number 2. Again I will repeat it. We have equation number 2 for k equals to 1 to n, so we sum all the n number of inequalities by adding the left hand sides and right hand sides of equation number 2, and we get this one, this result. Okay, so then we have summation k from 1 to n mod xk mod y k whole divided by summation I from 1 to n mod xi power p whole power 1 by p summation I from 1 to n mod yi power q whole power 1 by q. This is less than or equal to 1 by p, and here you can see that we change the indices, and here also in the numerator we change the indices. We replace k by I because uh, here this quantity and this quantity, the answer is same. Also the sum of all these terms, y k mod whole power q, and the sum of all these terms, the sum of all mod yi power q is the same. So these two quantities are same, so we replace k by I, so it doesn't matter because the answer is same. So we replace k by I. When we replace k by I here, what happens? I from 1 to n mod xi power p divided by the same thing plus likewise summation I from 1 to n mod yi power q. So ultimately we have summation k from 1 to n mod of xk into mod yk whole divided by summation I from 1 summation I from 1 to n mod xi or p whole power 1 by p summation I from 1 to n mod yi power q whole power 1 by q less than or equal to this equals 1 and this equals 1. So we have 1 by p plus 1 by q, and what is the condition? 1 by p plus 1 by q in the beginning, uh, we suppose that that's equal to 1. This is our condition. If you can see, in the beginning we take 1 by p plus 1 by q equals 1, so that's equal to 1. So this implies that, and we also replace the indices here. We replace k by I. I from 1 to n less than or equal to sum of mod yi power q where I starts from 1 to n whole power by q. So what we did, we just replace the indices, we replace k by I, and we can replace it, it doesn't matter, because this is the sum from k equals 1 to n. So uh, we replace the indices, we might have I from 1 to n. So we just replace the indices, we replace k by I, and ultimately we have the required Hölder's inequality, which is required Hölder's inequality for finite sum.